The total mechanical energy includes kinetic energy and potential energy. The kinetic energy is 1/2 mv squared, and in this unit, we have two kinds of potential energy, gravitational mgy, and the spring's potential energy 1/2 kx squared. So if an object is moving, then we have kinetic energy. If an object is not on the ground, we have mgy, and if there is a spring that is either stretched or compressed, we have 1/2 kx squared. In an energy conservation problem, if there's no air resistance or friction to take energy away, that means the total mechanical energy is conserved. Let's say you have a projectile that's shot from the top of the cliff and lands down low. The initial speed and the height of the cliff are given, and we're looking for the landing speed right here. If we ignore the air resistance, then the mechanical energy is conserved. In this case, initially the projectile is moving, so there is kinetic energy. It's up high, so there is mgy. At the end, it's down low. There's no mgy, but it has 1/2 mv squared. Of course, that's the initial, that's the final speed. Then we can plug in the numbers and then solve for the final speed. Or we can have a projectile that's shot down low and then land up high. In that case, we do the same thing. Over here, we have kinetic energy. Up there, we have kinetic energy and potential energy. We set these two sides equal to each other and then solve for our unknown. Or we can have a pendulum released from rest over here and then swings down. And let's say we want to find the speed at the bottom of the swing. If we choose the lowest point of the problem as the ground, then over here at the beginning we have mgy. It starts from rest, so no 1/2 mv squared. And at the end, it's down here on the ground, the reference point ground, so there is no mgy, but it's moving, so we have 1/2 mv squared. The tricky part for this problem is the y. The height is the height above our ground, so this is the y we want. So to find the y, we can say this is the length of the string L, and we can find this distance. If we look at this right triangle over here, that's adjacent to the angle, so that part is L times cosine theta. So the y we need for this is L minus L cosine theta. You may have a roller coaster on a track, and you're given the speed here, and you're looking for the speed over there. Same thing, if there is no friction or air resistance to take energy away, then the mechanical energy here equals to the mechanical energy there. And in this case, if we choose the lower point over here as our reference point ground, then initially we would have mgy and 1/2 mv squared. And then down here, if this is the ground, then there is no mgy, there is only 1/2 mv2 squared. And then we can plug in the numbers and then solve for what we need. In this case, the y, since that is our ground, that means the y here is this height. Of course, you can also choose this as your ground. In that case, the mgy would be this at the beginning, and then there would be mgy at the end also. This will be the y at the end. You may have a cart pushed into a spring, compressing the spring a certain amount. Then you let go, and the cart gets launched and moves off at a speed v. Or it can go backwards like this. A cart moving at a speed v runs into the spring and compresses the spring a maximum amount. If there is no friction or air resistance to take energy away, then the total mechanical energy is the same before and after. And so before, the cart is at rest, no kinetic energy, so there is only 1/2 kx squared. Afterwards, the spring becomes relaxed, no more energy stored in the spring, and we have 1/2 mv squared. And then in this scenario, it's just that this is the beginning, 1/2 mv squared, and then when the spring reaches the maximum compression, it's the turning point for the cart, so there is no speed, no kinetic energy, and we only have 1/2 kx squared. So one of these will be an unknown, and then we can solve for it. Or you may have a vertical spring. You push the box into the spring and then release it. When the spring becomes relaxed again, the box gets a speed v, and then it continues to go up, and it reaches a maximum height. If there's no air resistance or friction to take energy away, then the total mechanical energy is the same at every stage. At the beginning, it's down low if we say this is the ground for the reference frame for mgy. Then there's no mgy here, and the block is at rest. So the only energy we have is 1/2 kx squared, spring's potential energy. And then the box is certainly moving, 1/2 mv squared, the spring is relaxed, no more 1/2 kx squared. But now the box is slightly above ground, so it has mgy, and the height above ground at this stage is x, because it goes back up by x. For the third stage over here, no energy stored in the spring. The block is at the maximum height, that's turning point, so no speed, no kinetic energy, and there is mgy. So we can just plug in the numbers and then find whatever we need to find. Of course, this can also go backwards. Let's say you release the box from rest over here and it falls down, and right before it touches the spring, it has a certain speed going downward, and then it compresses the spring a maximum amount. And it's the same thing. You may see a problem that involves a completely different scenario, but that's okay. You just have to look at what types of energy exists at every stage. You may also see problems involving forces and energy conservation. For example, you may be asked to find the tension in the string at the bottom of the swing, or you may be given the radius of curvature at the top over here and be asked to find the normal force on the roller coaster. In those cases, you can first use the conservation of energy to find the speed, and then draw the force diagram and then write the force equation. If there is air resistance or friction, we would lose mechanical energy, and the lost mechanical energy would turn into heat. In this case, the final mechanical energy would be less than the initial, and the difference is the heat produced. Or we can use the work energy theorem. The work done by the non-conservative force, the air resistance or friction, equals to the change in mechanical energy. In this equation, because the air resistance or friction takes energy away, the work done is negative. Since the mechanical energy decreases, the delta E is also negative. Then we talked about power. Power is work or energy transferred divided by time. So the unit is joules per second or watts. Because work is also force times displacement times cosine the angle between the two, power is also this. And most of the time for power problems, the cosine part here is 1. And the displacement divided by time, that's velocity. So in this case, power is also force times velocity. Because power is the work or energy transfer divided by time, that means power is the rate at which work is done, or the rate at which energy is being transferred. So if we're given the power and the time, then we can find the total energy being transferred. This will be power times time.